Okay, let's get started. We're trying to finish the IR spectrum first, and then I'm going to spend some time review the mechanism. Week 8, our expectation would be you can solve an NMR spectrum by yourself with the formula we provide, maybe under the hint of IR spectrum. So there is a stepwise approach. If you don't know what I'm talking about, go to the exercise, which is the example that I'm going to use today. This practice spectroscopy compound A, we're going to solve this one together. So we're going to give you the compound, NMR and IR. So you can think about what you're going to do if you only have those information and you're going to give me a complete structure. We're going to give you points on how close your compound is to our standard. I'm always going to use 10 points for a whole NMR spectrum. Degree of unsaturation, which is the first step, is always going to be 2 points because it's a very standard formula. So here is the formula. You need to memorize that because it's not very hard, and also because it's very useful. Why there is no oxygen? So where is the oxygen? We don't have oxygen in the whole formula, which means oxygen is not going to affect your degree of unsaturation. And when you calculate that, and when we see a correct calculation of degree of unsaturation, that's usually 2 points. I know it sounds disappointing, but that's what I told my student to. Don't spend too much time in NMR as well, because it's only 10 points. Go grab the rest of the 19 of the midterm. And these 2 points is the place that I only encourage my student to grab, because it's definitely going to be yours as long as you can do the easy math. So that's the only step that I encourage my student to do. And then how about the rest? Well, let's see how far you can go then. So when you know there's a degree of unsaturation, you're going to get the hints from, is there a double bond? So see the name. So if it's a double bond, it's going to have degree of unsaturation of 1. So I'm going to list something later in the exercise. So you're going to get the idea what I mean by that. But just the formula and the correct calculation, it worth 2 points. And then the second step would be IR. Did you still remember that in discussion 5 that I told you that it's actually more important to see what is not in IR? So it is very important to search the functional group that are present, but it's also very important to highlight what is not in IR. Because that's going to wipe out a lot of the possibility in NMR spectrum. So these 2 steps are kind of the easy step. And then when we go to the proton NMR, even we haven't started, we kind of have an idea of what kind of functional group that we are looking for. And we also know there's a table or there's a chart of what each functional group should lay on in proton NMR. So that's kind of where you should get started. Here is the stepwise procedure of Professor Sarah Levens, because I told you Sarah Levens basically writes the whole discussion manual. You can follow her way because she actually has her own video on YouTube talking about how to solve an NMR problem. You can use the way that she's listed here, but as I told you before, as long as your structure is correct, you doesn't have to follow her method. So I'll just leave the rest of them on the discussion menu. I'm going to solve the compound A with you, and I'm going to show you how I think in each step. But the space on discussion menu, see, there only this much space. It's not going to be enough for me. So I copy and paste this one to another page.
Let's first start with degree of saturation. In our case, the formula is C8H17BRO, So let's plug in. You can tell what kind of functional group does this compound have by just calculating the degree of unsaturation. For example, double bond and ring both have degree of unsaturation of 1. So it would be easy to guess if we have degree of unsaturation of 2, then it can be 2 double bond, or 2 rings, or triple bond, or 1 double bond, 1 ring. When you see degree of unsaturation of 4, that's usually a benzene, which has a ring and 3 double bonds. So let's continue with IR spectrum to see what kind of information that we can read. So keep in mind it's actually more important to see at what is not in IR. For example, here, we cannot see a hydroxyl peak. That means it doesn't have hydroxyl peak. And the same with the triple bond. So no triple bond, no double bond. Let's write down the hints next to our IR. So no hydroxyl, no double bond, no triple bond. But pay attention to what we have in the formula. There's an oxygen. So what are the combination of oxygen then? So it can be an alcohol or it can be an ether. But we already know that we don't have an hydroxyl peak in our IR spectrum. So it cannot be alcohol. It must be an ether. Okay, let's just remove them here. What I'm going to do now is going to transfer the information from proton NMR into a list of table. Let's start with the doublet. So it's between 0 and 1 ppm. So I have a 1 neighbor methyl group, CH3, right? Because there's 3 hydrogen and it's a doublet. And what else do I have? There's a triplet. Okay, so it's a 2 neighbor CH3. Okay, let's speed up a little bit. We all follow the n+1 rule. Okay, it's done. Now I'm going to just copy this table into a blank piece of paper because I have transferred everything I need from proton NMR into this table. So basically, I do not need the proton NMR spectrum anymore. Now it's the time for solving the puzzle. Let's start with the hydrogen with only 1 neighbor. This only 1 neighbor CH3 must be bonded to the only CH in the whole group. And let's see how many neighbors does the CH left. So previously it had 7 neighbors, but now because I have a CH3 next to my CH, so 7 minus 3 equals to 4. So I only need 4 more hydrogen neighbors. And we also know 4 equals to 2 plus 2 and 3 plus 1. Since we don't have any CH in the group anymore, so no CH anymore, that's wipe out this possibility. It has to be 2CH2. So let's change this 4 into 2CH2. So let's continue. What are the other groups that can be linked together? So let's see this A, and then what else? It has 2 neighbors, and I have a bunch of CH2 next. So who is my neighbor? So we have 3 different CH2 has 3 neighbors. So this CH3 is the 3 hydrogen neighbor of this A prime CH2. Now what we need to do is to choose one of them and link it to my methyl group for now. Also because the CH2 only have 3 neighbors, which means on the other side of this CH2 there should be no hydrogen neighbor. And it's highly likely to be something very electronegative. Similarly, let's combine the other CH2 together. So there are some possibilities. Just by observing what we have, we know that it's either going to be a CH2 bonded to a CH2 with 2 neighbor, or a CH2 bonded to a CH2 with 3 neighbor, which means apart from the only CH2 I have, there's one more neighbor needed. Let's try the first one and see how things going. So if I'm linked with possibility A, then this compound ended here because we cannot link our first group together with this one, right? So it's not possibility A. So let's copy and paste the other two groups down here and start to try how is the possibility B work here. So if I'm collecting this cyano group with my purple group with an oxygen, then it meets the requirements of both and is electronegative and no neighbors. Now I'm gonna to connect the other blue group with my cyano group, and it's very obvious that the only one hydrogen neighbor that I'm looking for my CH2 is the one of my only CH. See, I'm color it in green and yellow. So the other side of my CH2 is going to be whatever left over, which is another CH2 and a bromo. Okay, let's put all the pieces together to see what is the complete structure of our compound.
I will send you this page. And in this question, we only go over to up to 4. But here, there is something else. Like in a range of between 6 to 8, it's going to be the hydrogen on benzene ring. And between 8 to 10, it's going to be aldehyde. Between 10 to 12, it's going to be carboxylic acid. So there are more things that you need to pay attention to. So if you don't know if you have did it correctly, so you are gonna just to draw the compounds you think it is, and in structure predict proton hydrogen. It's gonna to give you the peak of the predicted compound. This is only based on the fact that you're going to have a open book exam and you have 2 days. So if you want to make your answer perfect, then you can put your answer in ChemDraw to check until you see something similar to what has been given to you. I'm still talking on my discussion 6 notes from my past experience. So that's kind of we're fall behind, or maybe just I'm fall behind. It doesn't matter. Okay. So I hope you all get a fully exercise on SN2, SN1, E2, and E1. By now, you should be it should be not very hard for you to differentiate which is a better nucleophile, which is a better base. So one here is going to be a strong nucleophile. How about if I'm changing oxygen into sulfur, and the reasoning actually is already on the right. So this is a strong nucleophile. And here OH is also a weak nucleophile. When we are discussing base, pKa of this one is around 16, while the pKa of this one is going to be around 7. Apart from a strong nucleophile, this is also a strong base, while chloro is a weak base. It's just a quick recall on that. I list the 4 kinds of mechanism on the left, but we all know for primary alkyl halides, because primary carbocation is not stable, we know that SN1 is not going to happen. So E1 is always going to be a side reaction of SN1. So whenever you have SN1, you're always going to write the product of E1 as a side product. Already wipe out the possibility of SN1 and E1. Try to write the answer, the major products of these two, the example 1 and 2. Okay, so let's work them together. OH minus is a good nucleophile and also a strong base. Okay, so in the first example, because SN2 is faster. It's faster. So SN2 is going to be the major product. So the product of SN2, you should be able to write them directly. It's going to be OH. And because I didn't show stereochemistry, so it should be anti-position. But because I didn't show stereochemistry in my question, so you don't have to show it. The first one is SN2. E2 happens. So SN2 win. Okay, the second one. The second one, is this a good nucleophile or not? So it's not. So if it's not, I'm going to just use a pink. So it's a weak nucleophile. But it's a good base. And it's a bulky base. So, well, in this case, so E2 is going to be the major product. So there are less SN2 because of the steric hindrance. This side is too bulky. So it's not very easy for the nucleophile to attack on center carbon. So in this case, the product should be elimination, okay? And that should be E2. So that's the major product, so E2. But you're also going to see some of the SN2, some, but this is minor. SN2. So this is major E2. If it's in the exam, you only have to show this. Okay. If it's tertiary, then that's also easy because we all know tertiary is very bulky. If the center carbon is tertiary, then we are not going to have SN2 because SN2 always hates steric hindrance. Either the nucleophile or the center carbon should be as small as possible. Okay, so in this case, the first one, so let's still go to our reasoning. So what our reasoning is. So this is a good nucleophile. OH minus is a good nucleophile. And it's also a strong base. But SN2, if it's SN2, there are too much steric hindrance, which SN2 is hate to. So it's actually going to be very hard to attack. So there will be less SN2. But E2 won't be affected. So the major type of reaction of this one is going to be E2. And it's going to look like this. However, if we change the strong base and good nucleophile into a weak base, and think about, so this is first, it's going to be a weak nucleophile. also a weak base. So if it's a weak nucleophile, it's going to be SN1. If it's weak base, it's going to be E1. But so just by when you see SN1, you know the good friend of SN1 and E1 is going to be here. But the reason SN1 is measured here is because we don't have heat, because E1 usually require heat, but in the condition it doesn't have the heat. So we know the major reaction of this one is going to be SN1. So you're going to write OH. The plus minus means there's a pair of racemic structure. And then E1, which is the minor product. E1, minor. SN1, major. Okay? So if it's secondary, all of those four would happen. All of those four would happen. It doesn't, so secondary would be the most difficult one to compare with, because all of them are possible. First one, SH, is that a good nucleophile? It is, so good nucleophile. If that is a good base, no, it's a weak base. So it's going to be strong SN2. And another good thing would be the polar aprotic solvents that is listed here. So I listed a bunch of polar aprotic solvents, which is also at the back of your discussion manual. Those are good favored, so favored SN2. Hurt SN1. Okay? So less base, so the weak base, less E2. So the major products for this one is going to be SN2, and it's going to be SH. And this is the only product. Okay? Okay, this is an acid. So this is an acid. So we know this is going to be a weak base because it's an acid. And this is also a weak nucleophile. But just because substitution is also always faster than elimination, then this is going to be SN1. The reason, another reason, is because the polar protic solvent favor SN1, hurt SN2. Okay? So here we know this one probably is going to be SN1. And at the product of SN1 is always going to be a mixture. So it's going to be O and dash. Okay. So there's also a minor E1 product, which I didn't write here. You can write it down if you want. This one, it's a good nucleophile, and it's also a strong base. So what would be happen? So if it's good nucleophile, it's going to be SN2. If it's a strong base, it's going to be E2. But let's look at this one here. What do we have? This is polar protic solvent, which is going to hurt SN2. So this one, E2 win. And the product, the E2 product is going to look like this. So base grab the anti-position hydrogen and kick the leaving group out. Okay, so this is major. And then there are SN2 as well. There are other elimination products as well. So you can write the rest of the elimination products. So that's a double bond, okay? And then also SN2. But this is all going to be meaner. If I'm not wrong, she actually combined primary on branch and primary branch together. I know you're going to have an open book exam, but I still think it's actually easier if you can have this table memorized or somehow keep in mind. So the way that I'm going to write this table as is not going to fill the whole table with box. I just need to remember where is the position of those words. So what do I mean by that? For example, I know no reaction for the first three. SN1, here, SN2, 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 E2, E2. So I don't have to memorize the whole table. I just need to remember where is their position. And then did you still remember we talk about in secondary nucleophile that if it's polar aprotic, it's SN2. If it's polar protic, it's SN1. So by using this table, it's going to be very clear which is which. But I think the hardest point would be know what is a good nucleophile, know what is a bulky or small base. Okay. So I know this week is kind of hard for you guys. These notes, I walked through them really quickly because I hope that you can rewatch the video, go back and slow down to see what my reasoning. Maybe not very possible for you to follow all the way through my logic, but the question I listed in the week 6, which is the notes that I'm using here, are some of the very common mistakes. So otherwise, I'm just going to waiting for questions. Do you guys have questions? And if not, then we are going to see you guys in office hour. Okay, then bye-bye then. Bye-bye.